And our next speaker will be, yes, will be Monika Brandic-Lipinska. I don't know if I pronounced it good. Okay.
Yeah.
So she will tell us about drop the base, biological ISRU-based aleatory construction system for Martian habitats. It will be also about biofabrication strategy for stabilizing regolith using mycelium. The floor is yours.
If you can just explain me how to share my screen, because
okay.
I don't see like down there it's open share menu or device settings. Sorry.
Okay, I will.
Like I was in this preparation room, but
okay. I will have to. Okay, can you see the open share menu?
Yeah.
And so.
Okay, see. Okay, it was enough to click it, and then I see. Okay,
yes.
Awesome. Thanks. Whoa. Okay. Okay, thank you so much for having me. You pronounced my name correctly. It's Monika Brandic-Lipinska. I'm a PhD student at Newcastle University at Hub for Biotechnology in Built Environment, where I'm working on, basically I'll show you what I'm working on. It's a design of Martian habitat out of mycelium and utilization of mycelium for alternative construction for extraterrestrial habitats. So how Niels presented pretty well, when we go to Mars, we cannot take as much with us as we can to International Space Station or even to the moon, because it's much, much further away. So we have these two construction systems that we're using right now, or we're planning to use right now. The first one is to bring everything from Earth, the same way as International Space Station was constructed. And the second one is in situ resource utilization. So basically the use of local resources. The first one, it's very cost efficient, very cost, it consumes a lot of costs because you have to take literally everything with you, and it's very costly to launch things from Earth. The second one also might be very cost consuming because of the machinery that we might need to process regolith, for example, to gather it, to sinter it, or create a 3D printing paste and 3D print and then assemble habitats. So thinking of building on Mars, we kind of need an alternative approach or something to add to these approaches to make it more efficient. And that approach could be growth. So having this possibility to growing habitats, we might have structures that are capable of responding dynamically to the environment and are capable of maintaining and healing themselves because they're living, so they might adapt and change. So the project that I'm working on started when I was back in my internships at NASA Ames Research Center in Lynn Rothschild's laboratory, where we were working on the project called Myco-Architecture of Planet, which was utilizing mycelium, which is a vegetative root part of fungi that you can see here on the pictures. It has this branching thread-like hyphae. And the idea was to use mycelium to build or grow the habitat. The approach that NASA is investigating and developing, it's standalone approach, or like based on inflatable structures. So basically you bring like a bug, inflatable bug, which is the habitat from Earth. You add water, sunlight, carbon dioxide, which all is present on the Mars. And then the structure grows and it's becoming filled with mycelium, and it creates this mycoshell structure. The approach that I'm developing in a parallel to NASA's project is approach in conjunction with regolith. So I'm trying to use mycelium as a reinforcement for the regolith. So while growing it, I want to use minimum amount of biomass because we don't really have the biomass on Mars. That's something that we would create when the humans are there, and we will have greenhouses. But also the ideal scenario is that we would have this closed loop life support system. So we wouldn't really have much waste that we can, or plants that we can utilize for other purposes. So here the idea is to use the minimum of biomass and just somehow grow mycelium within the regolith, so it reinforces the structure. So the way how it works, the way how mycelial components work is that mycelium, this vegetative part of fungi, secrete enzymes that dissolve their food and bond with the substrate on a cellular level. So you can take any kind of organic substrate like beechwood or sawdust, anything that is lignocellulosic based, and mix it with mycelium and then put it into some kind of formwork. And then after a certain time of growth, you have structural components. And here on the bottom, you can see many different variations of that. It's either bricks or like panels or smaller elements or 3D printed mycelium. So you can, it gives a lot of possibilities of what you can actually achieve. And it has a very great properties, and it's been used on Earth for more like for artistic installations and small architectural pavilions rather than actual buildings, but it's also used for thermal insulation, for example, because it has a very great thermal insulation and fire resistant properties. But what is the most interesting for use of it in space is that it's self-replicable and self-healing. So we can take just a little bit of it with us and then replicate it in destination. So the idea is that we would use mostly regolith, which is abundant on Mars. And then for this organic substrate, that would be waste from the greenhouse, but just the minimum of it. Or it could be also like an algae or cyanobacteria that could feed on carbon dioxide present in the atmosphere, produce oxygen, and then mycelium use that to grow as a nutrition source, but also as an oxygen source. The other actor in this play would be mycelium that would have to be brought from Earth, but again, it could be replicated in situ, so we don't need really that much to take with us. Sunlight, not really necessary for mycelium growth, but in case of cyanobacteria, we might need that. Carbon dioxide, water, and oxygen, all present on Mars, or could be somehow extracted or processed. And then finally, we need some kind of casting, biowelding strategy of how to actually make structural components out of these elements. So this is what artificial intelligence shows when I typed mycelium-based habitat on Mars. And what I'm working with, it's a little bit more bottom-up approach. So I'm trying to figure out if it's even possible to grow mycelium or regolith and how it's might interact with each other and what are the mechanical properties, and later on how it might translate into creation of the structure. So the goal of my research is to develop a biofabrication strategy for stabilizing regolith using mycelium to construct inhabitable structures. And what is really important is that it's in resource limited conditions. So again, I'm trying to minimize, for example, the biomass. And that approach responds to a lot of different goals connected with human exploration of space and especially Mars, which are associated with creation of the habitat. So for example, reliability, long lifespan, planetary protection, where here it would be an additional issue to solve because we're introducing living material. So we have to make sure that there is no forward or backward contamination, and we're not spreading this new form of life on the Martian surface. And the other thing is the mass brought from Earth, that we're saving what we need to bring with us. And it gives us flexibility because we can grow the habitats or extend the habitats while the mission progresses, or with new mission types and mission needs, we can adapt the habitat to the needs. There are additional aspects that in a far future, they have to be taken under consideration, and to make the project actually work on Mars have to be taken under consideration, like environmental conditions, the chemical composition of actual Martian regolith, the nutrition source, because it will differ if we're using parts from the greenhouse, or it will differ if we use cyanobacterial algae, and then finally mycelium species. So how to choose mycelium species nutrition source that will be in the symbiosis with the regolith and working also in this extreme environments. We wouldn't grow it just like that on the surface because, again, planetary protection. So there would have to be some kind of closed environment providing the right temperature, right pressure, but still these 4 elements have to work in a symbiosis and they have to be carefully chosen. Right now, I'm working with Ganoderma lucidium, which is one of the popular mycelium species used for architecture purposes. And for now, I'm working with sand, so not really regolith. So it might change because of the grain size and chemical composition. But I wanted to see if it's even possible and how the structure works and the interaction between these two. So I started with doing experiments growing mycelium on sand with a little bit of beechwood on petri dishes. And here you can see under the microscope that it literally holds the grain particles together, and it holds the structure together by the way how the mycelium tangles around these grain particles. So there is not really chemical interaction, it's just mechanical how it literally holds it. So I was having this different discs of mycelium. Some of them were working, some of them were not. You can see this one, for example, it's pretty flexible. And then after I figure out how to make this on a small scale, I moved to a bit bigger scale of a column, where here you can see this is 90% of sand in terms of the mass of the weight, and 10% of mycelium with biomass. So it's mostly sand structure that it's made and held by mycelium. You can see that it grows much more on the outside rather than the inside. There is still some growth on the inside, but what I observe is that mostly it's held by this, I call it like a graded surface binding, how the mycelium grown on the outside holds it. It's almost like a bug holding the sand inside. So there are these 3 levels of interaction. The first one is internal network, how it stabilizes the structure, how mycelium grows inside. The second one is the surface binding. And then finally, it's the biowelding, so how the structure composed out of different elements holds together. And how we can construct that on Mars. So this is, again, what AI shows us. And in the case of biowelded mycelium-based habitat, probably it again has to be taken step by step rather than big construction site. So one of the ideas is to use interlocking elements. So here you have an example of the elements that they don't need any additional binding agent. They interlock and they stay together based on their geometry. And the idea is that on Mars, where we have lower gravity, we cannot really rely on elements being held together for a long time, because these topological interlocking systems basically rely on the weight of the elements, how one holds another. But if we have biowelding qualities where the elements can grow in together, then with this topological interlocking, we can have a structure that it's put together and then over time grow in together, and we have a solid structure that won't break. So here again are some experiments that I was doing. The first ones with this interlocking shapes and how they might grow together. And now I'm looking into 3 aspects of how to actually design the best geometry for such project, for such conditions. And there are 3 aspects that I'm looking at. So the first one is fabrication process. It cannot be too complicated. It cannot be a very complex process. It cannot be a very complex mold, because eventually doing it on Mars, ideally automatically, it has to be as simple as possible. The second one is aggregation process.
May interrupt?
Yeah.
There are only 2 minutes left.
Yeah, that's perfect. Thanks. So the second one is how these elements are coming together, how it works structurally, how, for example, you can have these elements that are almost like self-assembling, or elements that are like brick by brick that have to be put together. So this aggregation process. And the third one is biowelding process. So how the elements can actually grow in together. So for example, we need the maximum surface contact. It cannot be point of contact, but the more surface to surface we have, the better the structure will grow in together. So it's basically this whole iteration and learning from the living material of what it wants to be and how it interacts, and through that getting into the ideal shape. So here are some ideas how the shapes may look like and how they might be like interlocking and really having this maximum surface to touch each other and to create structures. So eventually it will be somewhere on the scale between putting bricks together where you need robotic operations to put it, all the way to self-assembly where you literally drop elements and they self-assemble together. So somewhere on that scale from one to another, these self-assembled interlocking aleatory structures will be placed. So it will be somewhere between building the habitat brick by brick and literally dropping the base somewhere here. And that's where I'm working on right now, and finding where it is and what exactly it is. Thank you. And I'll be happy to take questions as well. And I don't know how to unshare my screen. Stop sharing. Okay. I cannot hear you.
And now? Okay, it's just the phone. Okay, so how do you choose the form in which you want to grow the mycelium?
So it's basically these three elements that I was saying. So I'm doing computational simulations, for example, of how different elements, the different geometries would interlock under Martian gravity, because they would, like, if you drop elements, they would drop differently in our gravity and in Martian gravity. So that's one, computer simulation. The other one is this, keeping in mind that it cannot be too complex, because I have to somehow, first thing I have to manufacture it here, but eventually it would have to be manufactured there. So it has to be simple. And then the third one is doing experiments with just growing, like, let's say I have two elements and growing them together and seeing how they perform this biowelding, if the surface is, like, you know, big enough, or they, so it's basically iterations of these three aspects, but it's iterations through like computational analysis and actual experiments.
I see. Thank you very much. The next question is, how would you like to solve the problem of replacing dead cells with living ones, especially since your system must be closed? And Mikołaj added, because you want to, in the same time, keep them alive, and because you mentioned building self-repair.
Yeah. So obviously, when we expose the habitat for like open Martian surface, that would kill the mycelium. Also, I'm not sure if we can do that from planetary protection point of view, because like technically it will be killed, but also we are exposing it. So I'm not sure. So yeah, it's a matter of planning if the habitat is going to stay alive as the whole habitat, and then the whole habitat would have to be somehow, you know, it's kind of like interior layer between, it's not the last layer. So there would have to be like a last layer keeping it from the environment. And then the whole habitat can stay living and performing different functions in further future, where we can have mycelium-based sensors and mycelium-based electronics, where the whole habitat would, like, you know, for example, give you information that it depressurized or the temperature changed. So then the self-replication could be performed as well, because we are assuming that the whole thing stays alive. If it doesn't, then it's a matter of probably you will have to keep part of it alive, and you use that to repair and like somehow plan the process of repairment, where you repair parts that are not alive anymore, just by adding the new parts. I don't know. I didn't get that far in, like, you know, planning the whole lifespan of the habitat and how it will function. But it's a good question to, like, it has to be solved.
So everything is behind you. Okay. So the next question is from Camille. Is there a possibility for synthetic fungi to thrive and proliferate beyond Earth?
Yeah, that's a great question. I'm not sure if I'm the right person to answer it as an architect, but I hope so. Like, we're looking into this melanin-rich fungi that could provide radiation protection, and it has been proved that they thrive in radiation and they grow towards radiation. So I imagine, or you have this fungi species that are found in Antarctica, and they can survive in a very extreme environment. So I guess it's a task for synthetic biologists to figure out how to make fungi that will just grow like that, thrive in Martian environment, do not contaminate Mars, give us radiation protection, and be able to perform all of these different functions to help the whole functioning of the habitat.
Okay, and another question also from Camille. Is it possible to create other space structures using mycelium, such as orbital hubs and satellite platforms?
So I think it's similar as with the differences between Mars and the Moon, that on Mars we already have carbon dioxide present in the atmosphere, and we have this regolith that is present. So we have more materials, more resources that we could use. I'm not sure if it would make that much sense building it, growing it as an orbital platform, because mycelium doesn't grow in a volume, in a sense that it wouldn't. It grows on the surface, it grows on something, and then it digests the substrate that it gives. So in terms of regolith, it grows between and it holds it together, but it doesn't really grow in a volume. So you would have to have something. If you have maybe like space station that doesn't have like a closed loop life support system, and you have a lot of like biological waste and you want to utilize it somehow, then that could be an idea, that you use mycelium to like digest it, and instead of just decompose it completely, you can create like interior elements, for example, furnitures, and I don't know. But I'm not sure if it would make sense for the whole habitat. Maybe. I don't know. If we'll figure out this mycelium species that can give you like full radiation protection, then yeah.
Okay. Another question from Matthew. The height of your structure is going to be limited by the crash force of your bottom row of bricks. So how tall could you theoretically make these structures currently?
Yeah, so I'm not sure. I haven't tested that yet, but my assumption is that it could be much taller than on Earth, because the gravity is much lower. So, you know, when you even like in case of dropping these elements, so you don't have to build big brick by brick, it just saves you energy, which is a valuable resource as well. So I'm assuming you can drop the elements and they won't crash that much. So also I'm assuming you can build higher structures than on Earth. The thing is that, okay, it is heavy because I'm using it with regolith. The regular components are not that heavy because they're just like biological beechwood based materials. So they're very lightweight. So even if you build high structures, they kind of sitting on top of each other, they don't put that much weight. Here, I hope that the lower gravity would let us do it pretty tall, but also it doesn't have to be super tall. I don't know. This part, like, I don't have figured out yet because I'm still on the part of the element shape and how they interact, and then later on it will, like, you know, it will be the actual structure. But if I'll manage to like build something that it's a human size, so you can go under, like an arch that you can go underneath, I would be already happy with that.
Okay. Another question from Mikołaj. So what do you want to add, replace in your fungi from a synthetic biology point of view? What there are missing?
Oh, okay. So the possibility to grow it in lower temperatures and lower pressure. The lower temperature we can get, the better, because then we don't have to, you know, supply the warmth when we're growing it on Mars. So that would be perfect. And yeah, I think radiation protection, that's the coolest thing, because if we can grow structure that it's literally providing the whole radiation protection that we need, then we don't have to cover it again with like layers of regolith or all of these ideas of going underground. Like, we can just build habitats wherever we want. So I think that would be like the best thing. And the other thing, I don't know, having it translucent, I don't know if that's possible, and having, like, you know, windows that are providing radiation protection, but they're grown. And this is probably too sci-fi, but why not? Synthetic biology is like basically sci-fi that it exists. So
fungi windows.
Yeah.
Okay. So there are also two last questions. Would it be easy to dissolve the structure using biological means and recycling the material in order to remove unused or abandoned structures?
Yeah, so this touches very interesting aspect of what it really means that things are biodegradable, because here on Earth, biodegradable things, they just decompose and that's it. But on Mars, like we cannot just biodegrade it, because then we contaminate Mars, and also the environment is different. So I don't know. I don't know how to answer that question. It's something definitely that is like back in my head when I'm thinking of this project, and in general of using biological materials, where one of the biggest advantages that it's claimed for Earth project is biodegradability. And I heard a couple of times people are saying that on space conferences, that things are biodegradable, but what it really means, like how you can biodegrade something on Mars and on the moon. So I don't really know, but this is...
Could we take some bacteria that would, like, we accidentally take a bacteria from Earth that would just eat our habitat? Would it be possible?
That would be really cool. They just clean after yourself, and like there's no trace of us being there. Yeah, that would be really cool.
Would it be really cool if it ate our base with us inside?
Well, maybe not. Hey, but that could be a possibility. Like eventually you turn in mycelium into like fruiting bodies and you eat your habitat. So it's basically like a Christmas gingerbread house just on Mars.
And what if the mycelium would start to defend and release some antibiotics?
And create intelligent life and take over Mars.
Could that release antibiotics make us allergic to it or something like this? It could just die.
Yeah, I don't know. I'm trying not to go that far, because then I'll think that it doesn't make any sense, and I'll think, my whole PhD, like maybe not. So yeah, I don't know.
Okay, so there's one last question, and would this approach be relevant for constructing structures here on Earth? And isn't the cell division time difficult to overcome limiting factor for this kind of material?
Yes, so definitely on Earth it's super sustainable like approach to construction, and it's already been used for this insulation materials. It doesn't have that much lifespan. So the idea is that it's biodegradable, and it's been presented as an advantage that we're not needing houses for 100 years anymore, because we're changing lifestyle and changing places, so it could be for shorter. But also in terms of architecture, I think it's a flaw that it biodegrade. So I hope that what I'm developing, which is this components with minimum of biomass, even if they stay alive for longer, they wouldn't degrade that much, because most of it's not organic. So maybe that could be a solution for providing this lifespan to mycelium structures, but then it loses this lightweight property. But yeah, it's definitely being researched a lot for terrestrial architecture, for these pavilions, and more as not used solely as like mycelium building, but as a part of it. So when you build a wall, like some part of it's mycelium, for example.
Okay.
Or insulation or acoustic panels and finishings, furnitures, and yeah, so it's much more popular.
Okay, thank you very much for the presentation.